us to discuss something that is predicated upon you actually having a decent understanding of what the topic is. And if you're using that analogy, you have no foggy clue what entropy is. And so, one of the things in every class I teach that entropy comes up in, and I'm warning you now, for those of you who are going to be seeing me for Physics 2 in the spring, you just think that I'm going to discuss entropy in here. We're going to discuss it for about 3 weeks, and in the physics context. But those things, and scientists don't do well communicating. It's not, it's in a lot of ways our own doing. We don't do well communicating to the general public about concepts. And so we've kind of created this problem ourselves, and now we're having to try to fix it. But we'll get there. The important one for the moment is, let's get rid of that idea of spontaneous, right? Because in analyzing a chemical reaction, there are two ways to look at it. You can look at it thermodynamically, and you can look at it kinetically, right? They are interconnected. They are interconnected through the concepts of entropy, particularly through something known as Boltzmann's constant, which we'll talk about. But they are distinctly different things. And I guess you can think of it, let's give you an analogy for the difference here. When you think about your life, born, and I assume none of you have died yet, all right? Sometimes I look at my students and I think they might have died, because they're just sitting there, and they haven't moved in an hour and a half. You are very, very concerned with what happens in the middle, right? Okay? You take an active role, and what you do today, right, influences what you're going to do tomorrow, next week, next year. In other words, as the old adage goes, life is a highway, okay? And the path that you take through life matters, right? It governs how you end up. Now, go back and think of it from your high school history classes. What did you do in history class?
Not much. Reading.
Do what?
Not much.
Not much. Well, odds are it was taught by a coach, and so you didn't do anything but look at the history of football. But let me think of one that I actually know the dates for right off the top of my head. It don't matter. You learned, but most of these people that you studied in history class, what was the only thing that you really cared about? They were born here, died here, right? You didn't really discuss a whole lot about what they did in the middle. All you cared about was where they started, where they ended, okay? That is a good kind of example of the difference between thermodynamics and kinetics. Thermodynamics are what we call state functions. The values of thermodynamic parameters are dependent solely upon the state that the system is in right then and there. Okay? It doesn't matter how it got there. Right? You don't really care how Columbus died. The fact that he's dead and not walking around 500-something years old is sufficient, right? You, on the other hand, probably care quite a lot about the method by which your demise occurs, correct? I mean, there are a whole lot of things that we would like to avoid. But thermodynamics are state functions. They depend solely on the state of the system at that moment in time. And changes in thermodynamic parameters are very easily determined. You've done it your entire scientific career. If I wanna know the difference, okay, if I wanna know the difference between floor level and here, what do? Take the height here, subtract the height of the floor, which should be 0, from it. Final minus initial gives me the change, right? Those are thermodynamic state functions. They depend solely upon the final and initial conditions of the system. They don't depend on anything else, right? And that's why but there's quite a few of them, and they are all intimately connected together. And ultimately, it is thermodynamics that will drive systems. Ultimately, thermodynamics wins. You can break a lot of laws, but you cannot violate the laws of thermodynamics. They win out in the long run, always. Now, process functions, on the other hand, are chemical kinetics. Chemical kinetics is more like your life pathway. You care a lot about how you get where you are. Okay? And you look back in time, just like the conversation we just had, sometimes you look back in time and you wish you could go back and do things. Right? Unlike life and chemical reactions, sometimes you can. But nonetheless, you care a lot about that pathway. And kinetics is the pathway. Right? Ultimately, there may be multiple pathways that a reaction can take. Thermodynamics will determine which pathway ultimately ends up winning out. Right? And we're going to discuss that quite a bit when we get to the thermodynamics packet. But for the moment, we want to go ahead and we want to deal with the kinetics side of things, and then we'll build in the thermodynamic parameters. Now, there's going to be a good bit of overlap, right? Because ultimately, if I've got a system and I can describe it with kinetics or I can describe it with thermodynamics, they're both still describing what? The same thing. So ultimately, they've got to have a tie-in. Somewhere, kinetics and thermodynamics have to come together and they have to mesh nice and neat and pretty. And they do. So we can start from either direction, but kinetics is the traditional starting point. But there is a good bit of overlap, and you do see several of the topics pop up. The first one, is what is known as the Gibbs free energy. Now, the Gibbs free energy, we're going to deal with extensively. It is a thermodynamic state function, meaning that I really only care about the final and initial positions. Gibbs free energy is most accurately defined as energy in a system that is available to do useful work. Not all energy can be used to do work. Some of it is going to get converted to heat. And you can go through, depending on what you're doing, you may use that heat later on to do something else, heat up a pot of water, and that water can do some work. But ultimately, as far as what is going on at that moment, any heat loss is wasted energy. The most common thing that we see that with is power lines. Power lines generate or electrical power, or electrical energy, however you want to think of it. The amount of heat generated is directly proportional to the amperage, right? Higher amps, more heat loss, okay? Which is the whole reason that we have something called a transformer. Because voltage does not play into heat loss, but amps does. And this is just an example. This is not testable. This is not a testable example. So I got a choice. If I've got a system, it's an electrical wire, I'm flowing current through it. I've got two things. I want to preserve as much of the energy as possible, as much of the free energy as possible, so that later down the line it can do useful work. In other words, I don't want to create heat. And so what we do is we trade off. All right? Voltage and amperage do this. As you can take the amps down by jacking the volts up. And voltage does not figure into the heat loss equation. So when you go out to that three-phase power line up there, and that thing's carrying 15,000 volts, right? But you have more amps coming into your house than there is in that high voltage power line right there. But you only have 240 volts coming into your house. This is one of the reasons why you go over there when you plug in 50 dozen things to an electrical cord and you max out the amperage of the electrical cord and you go grab it, cord's what? Hot. Because you're pulling amps and amps directly relates to that. All of that heat is electrical energy that has been converted over to heat loss, and it is no longer available to do useful work in that system. Now, it may get transferred to another system, pot of water on your stove, all right, and get absorbed by that system and be able to do work. But you never recover all of it. You always lose some. But the Gibbs free energy is the amount of energy that is available to do useful work. And you say, well, that doesn't make any intuitive sense. What other energy would there be? We've spent a good bit of time leading up to this when we talked about bond strength, right? And how it takes energy to make a bond. If you break the bond, it releases energy, ionization energy of electrons, all that other stuff. But go back now. We also talked about nuclear forces, just briefly, where the protons and neutrons are stuck together. All of that requires energy, but that energy is not useful in chemical processes because it's not accessible. Think of it as the difference between hard and soft assets. Soft assets would be like the cash you have in your pocket, readily accessible and you can use it. Hard assets would be your certificate of deposit. It takes a couple of days for you to go in there, process the paperwork, and get your money. Okay. Same idea. So Gibbs free energy is the amount of energy in the system that's available to do useful work. Now, I'm going to reiterate something I mentioned day one. Positives and negatives in chemistry and physics imply flow direction. They're not, you gotta get away from the traditional thought process of if it's negative, I have less of something. It's talking about flow direction. Spontaneity of a system is determined by the Gibbs free energy as far as the explicit parameter. When you calculate the change, and with thermodynamic state functions, what we're interested in is the change in that parameter. The change in the Gibbs free energy from one state of a system to another. So, say a chemical reaction. And that's what's actually demonstrated here on this diagram. Take a chemical reaction. There it is. All right. And we're going to mix two things together. The horizontal axis is what we call the extent or the reaction coordinate. In other words, it's how far along the reaction is. It's a time parameter. Are we just beginning? Did we just mix them together? Or are we in the middle of the reaction, or are we towards the end of the reaction? This is the Gibbs free energy. Now, not delta G, this is the absolute parameter. At the beginning of the reaction, your reactants will have a certain amount of energy that is available to do useful work. Now, two possibilities exist. We'll talk about what this hump is in a minute, okay? This is where your reactants started. One possibility is that your products, when you do the free energy calculations, that the products have a lower level of free energy available than the reactants did. And quite simply, the reactants have more energy than the products. All right. Delta G, which is the parameter that we are interested in, is that gap between the free energy levels. Right? What value is this going to have? All right? G final minus G initial. Which one's bigger, G final or G initial? In this case, G initial is larger in value. All right? So delta G in this case is going to be less than 0. Now this is where entropy comes in, okay? Entropy is not about disorder, it's about energy dispersal. This one has a highly concentrated energy. This one has a far more dilute dispersed energy. And so this reaction, this is where intuition breaks down. Delta G less than 0 is actually a spontaneous reaction. Meaning I don't have to put energy into it. Think of a ball, think of gravitational energy. Gravitational energy, the ball at the top of the hill, does it need any help to roll to the bottom? No, it'll do it on its own because the bottom of the hill is a much lower potential. This is the same thing. The products are at the bottom of the hill. This reaction will go on its own without any help, right? Look at the other. G, extent. All right. So this one I said was spontaneous. What do you think that one's going to be? Non-spontaneous. Give me a thought. Use the logic here. If this one is spontaneous, what are we going to see on the non-spontaneous one?
Goes up.
They're going to reverse, right? You're going to get something that looks like that. In this case, it's always final minus initial. Even if your ultimate end formula ends up with something that you say, I just don't see how final minus initial came out of that. If you go back to the parent formula, it's final minus initial. There may be a double negative that pops up, or something like that, but it's final minus initial. In this case, which one's larger, final or initial? Final. So delta G is going to be
bigger,
positive, right? All right. Look at the graph, okay? You're at the bottom of the hill. How do I get a boulder to the top of the hill? Push it, all right? Gotta do what? And by pushing it, what am I putting into the boulder? Energy, okay? I may have to heat this reaction up to get it together. Right? Oh, ever put, all right, this is something everybody in the Deep South is familiar with, sweet tea. Right? People down here picky about their tea. Is it easier to sweeten tea when it's cold or when it's hot?
Hot.
When it's hot. Oh, y'all knew that answer. All right, now we're getting into something we're familiar with here. Okay, you go to a restaurant, you order some tea that they always got unsweet, but we'll bring you some sugar. And you go, just bring me some water. I'll drink water. Why? Because what's going to happen when you dump that sugar in that cold tea? It's going to go, and it don't matter. You can try to stir it. It's not going to dissolve. Okay. The solvation of sugar is temperature dependent. At cold temperatures, it looks like this. Okay. You got to put energy into it to make it get to that state. and solvate like you want it to do. Which is why, here in the Deep South, when we make tea, when do we put the sugar in? When it's on the stove, right? Preferably even before we put the tea bag in. Oh, heck with the tea bag, we just drink sugar water. And, like a bunch of ants. Now y'all are laughing, come on. All right. It's our Friday, we're good, we'll make it through. Anyway, so these are spontaneous, these are non-spontaneous. Now, this is where intuition is starting to break down, because right off the bat, you would have thought that that one would have been the spontaneous one, because you are accustomed to do. You think of spontaneity as being what I want to occur, and you think of positive numbers as being the numbers that you want to deal with. We gotta break all of that. All of your natural intuition doesn't hold here, okay? It's all about final minus initial on every one of these things. Now, did I ever say that this was going to be fast? No. All right. Delta G simply tells you whether or not a system left to its own devices will do something or not. It doesn't say anything about when it will do it or how long it's going to take. It simply means that it has the available energy to execute the process without you doing anything else. All right? Let's talk about carbon for a minute. Think about carbon. Carbon is, as we've already alluded to, carbon is very, very useful, very highly versatile element. Okay. Now, the same carbon that makes up your pencil lead, makes up the graphite in your pencil lead, is also the same carbon. It is that makes up that $10,000 diamond that's sitting in the jewelry store. The only difference is that the carbon in your pencil lead is the amorphous solid form of carbon. The diamond version, that highly expensive diamond version, is nothing but a rigid crystal lattice of carbon. Highly ordered. That's what I tell everybody. I buy a box of pencils and they say, what do you have there? I'm like, I got a bunch of pre-diamonds. They're just not put together. They're not. But it is a highly, somebody had to put something had to put a lot of energy. Usually we're talking about geothermal processes that put a lot of temperature and a lot of pressure to cause these things to crystallize. They're absorbing energy and they can get into that higher energy state. And it produces a diamond. Now, the one thing that Kay Jewelers got wrong in their commercial, diamonds are not forever. Right? The decay process, not the formation. The formation of a diamond looks like this. The decay of a diamond looks like that. All right?
Is it just extremely slow?
Bingo. It is extremely slow. All right? As in, you can have 1,000 lifetimes and you're still not going to observe it decay. But the free energy difference between a diamond and a pile of pencil lead, which is what it would decay to, is huge. It has an enormous delta G, or an enormously negative delta G. But the decay process is so kinetically slow that you will never observe it in 1,000 lifetimes. So spontaneity has nothing to do with speed. As a matter of fact, the vast majority of the biochemical processes in your body, if you take all of the catalysts, all of the which are enzymes, out of your body, and you figure the delta G for a good many of them, you find they're spontaneous. But if you take the catalyst out that speeds up the reaction, they do not occur even over the human lifetime. It takes the catalyst to shorten the time frame. And that's why biological enzymes are such a critical component of the human body. And so you have processes that left to their own device, they will go. It will eventually happen given enough time. But you may not be able to observe the rate. Yeah.
It's kind of a weird connection, but is it like that's why you can't build a person, you can't put a bunch of elements that make up human body in a pot and it just forms a human? Is that kind of like why?
Yeah. Yes. Because and I'm getting ahead of myself, but you're dabbling into something there that is a very important topic. And it's actually the topic of what entropy is. But let's say you take atom for atom, the elements that are in the human body. You figure it up and you say, okay, on average, there's this many carbon atoms, there's this many calcium atoms, yada, 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 you see my point, okay? And, take all the water out, the average human is only about 2 pounds of chemicals, right? And you cook this in a small teapot, right? The water is what gives you most of your substance. The arrangement of those atoms that is a functional human actually, and this is what throws people with entropy, so I don't want to get too deep into it just yet, is actually no more statistically unlikely than the arrangement that's just a pile of atoms on the floor. The difference is that the number of arrangements that give you a functional human being is about a gazillion times less than the number of arrangements of those molecules and atoms that just give you a pile of shit on the floor. All right? Go back to the marbles in the bag from elementary school. You've got 1 billion red marbles and 1 blue one. The 1 blue one is a functional human, okay? The likelihood of you pulling out any one marble in its own right, you got if I specify pull out a marble, the probability that any one marble will be the one that you grab is 1 out of whatever, right? If I add the additional constraint, pull out a blue marble, then the probability plummets. And so it compares, you gotta compare how many of them are these highly ordered states versus how many of them are the just piles of Schmitz, okay? We're gonna talk more about that. But yes, you are exactly correct. The highly ordered state is gonna have this, all right? Because you've got to put things together, you've got to build proteins and things like that. Now, y'all, I never have figured treading off into this. And I'm not about to start.